Hi, everybody. Welcome to our discussion of the fundamental theorem of calculus, or really the two parts of the fundamental theorem of calculus. I really like to call this section, the great calculus miracle, because what we're going to realize in this section is that the ideas of definite integrals and indefinite integrals really are connected. They're not just, we're just giving two things the same name, just, to get a kick out of giving two weird things the same name. They really are deeply connected, and we're going to see how. So, the first part of the fundamental theorem goes like this. Suppose that we have a nice continuous function on some interval a, b, and we look at the integral from a to b of, say, little f of x dx. Then we can actually get a number, right, that tells us the value of that integral by doing something really cool. What we do is we find an antiderivative, the capital F here. All we have to do is find an antiderivative, capital F, for the original function, little f, that we're integrating. Then plug in the two numbers that form the limits of integration. The top number, we plug that in first, then minus and plug in the lower limit. That's it. Really cool. So finding the value of a definite integral now just becomes a matter of, well, using an indefinite integral, or another word for that was antiderivative. We need to find an antiderivative and then plug in the value of the endpoints and subtract them. That's it. Now, there's a really cool notational trick that we'll use here to make things easier when we actually start doing examples. A lot of times we'll write that difference, that f of b minus f of a, as f of x, and then put a little bar, and then put an a at the bottom and a b at the top. That's notation that means plug in the b minus plug in the a. Right? So let's see how this would work. Right? So suppose that we have a definite integral from -2 up to 1 of 4x dx. Okay? So all we have to do is find an antiderivative for 4x, then plug in the 1 minus what we get when we plug in the -2. Okay, so antiderivative, or indefinite integral, right, for the antiderivative for the 4x, that's just going to be 2x squared, right? Now we need, so this is the reason, we see here where the bar comes in handy when we're handwriting one of these problems and solving it by hand. I would do my antiderivative, I'd write 2x squared, and I've written down the indefinite integral, and so it's too much trouble now to go in and just plug in the endpoints, the 1 and the 2, because I've already written 2x squared, right? And if I knew what the antiderivative was going to be before I wrote it down, I would have written it down. So I've got the antiderivative written down with x's in it. I need some way to say, oh yeah, but I've still got to plug in the endpoints, the limits of integration, I mean. So this is where that vertical bar, and then write a -2 at the bottom and a 1 at the top. That's our notation that says I've still got to plug in my endpoints. So I do. I plug in the 1 and then a minus sign, and then I plug in the -2. So 2 times 1 squared minus 2 times -2 squared. And if you go through and do all the squaring and the arithmetic, that turns out to be a -6. So simple, right? This is not hard at all. And this connects now the idea of a definite integral and an antiderivative. Let's do another example. Let's find the area under the curve of, given the curve y equals cosine of x, on the interval between -pi/2 and pi/2. Now, first off, remember, in order to get the definite integral to tell us this kind of an area, the function had to be sitting above the x-axis, and it is. Remember that the graph of cosine is positive all the way between -pi/2 and pi/2. So how do we do this? We write down our definite integral, and then we just evaluate it using the first half of the fundamental theorem. So what I need first is an antiderivative for cosine. We think back, how should that work? And that's going to be sine. If you're not sure which way it goes, whether this should be sine of x, or maybe it should have been minus sine of x. Remember, sine and cosine sometimes give you a minus sign when we're taking the derivatives. I always have to stop here and ask myself, let's just go backwards and check. So what's the derivative of sine? Oh, well, I know the derivative of sine is cosine. So perfect. then my antiderivative for cosine will be sine. No extraneous minus signs happening in there. Then I draw my vertical bar and write negative pi over 2 at the bottom and pi over 2 at the top to remind myself I still have to plug those limits in. Then I do that. It's sine of pi over 2 minus sine of negative pi over 2. Well, it turns out, of course, sine of pi over 2, that's 1. Sine of negative pi over 2, that's negative 1. So I'll get 1 minus negative 1, which means I'm really adding 1 and 1 to get 2. And that's it. Super easy. Let's try one more. So here's a definite integral from 4 to 9. And I'm integrating 1 over square root of x plus x. So how do I evaluate that? What I mean is figure out the number, right, that should give me. Well, first thing I need to do is rewrite that square root so that it's x raised to a power, right? That way I can use the power rule when I find my antiderivative. So that's a square root, which makes it x to the 1/2 power, but it's in the denominator, so that means it's negative 1/2 power. Right? Okay. So I'll have x to the negative 1/2 plus x, and I've got to find an antiderivative for that. And again, remember, I can do each piece separately. I'll do the x to the negative 1/2, and then a plus, and then do the x. So x to the negative 1/2, I would have to add 1 to the exponent, which means negative 1/2 plus 1 gives me a positive 1/2. So I'll have x to the positive 1/2 power, and then divide by the half. Then for the x, of course, that's x to the first power, so I add 1, which gives me x squared, and then divide by the 2. Now I draw my vertical bar with the 4 line. Isn't that vertical bar handy, right? It lets you work out the antiderivative with the x's in it, then notate that, oh, I've still got to plug in the endpoints, so I don't forget to do that. So I plug in the 9 everywhere there was an x, minus sign, and I plug in the 4. Be really careful here that you put parentheses around the two parts so that you don't accidentally mess up with that minus sign. See, that minus sign is going to have to distribute all the way through that parentheses, or I'm going to have to work out what's in parentheses first before I do the subtracting. So you have to be super careful not to make a silly arithmetic mistake here. As we go through, we start squaring stuff and blah, 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 and we end up getting something like 69 over 2. Okay, so why in the world should something like the first half of the fundamental theorem be true, right? I mean, why does this work? I think we need at least a brief explanation. And so if you'd asked Isaac Newton, he would have said something more or less like this, that if you think back how we talked about velocities and distances that were traveled by particles when we first started talking about definite integrals. Well, suppose that my f of x were a velocity, okay? Then this definite integral, right, between a and b would be telling me how far the particle traveled, right? When you integrate the velocity, we've seen several times that should give you the distance that the thing traveled. Okay, well, what about on the right-hand side of this equation? In other words, if I find an antiderivative for my function and plug in the b minus plug in the a, what's that really telling you? Well, if my function were a velocity, the antiderivative for that, away, right? That would have to be the position. Because remember, velocity is the derivative of the position. So if you give me the velocity and I go backwards, right, then the function that I get going backwards, right, to find an antiderivative, would be the position function. That capital F is the position function. So now what do? Well, I plug in the b, that's the endpoint where I stop, minus I plug in the a, that's the point where I started. So what I'm really doing on the right-hand side of that equation is finding the difference between where I stopped and where I started. And of course, that's got to give me the distance the thing traveled. So this is really just two ways of saying the distance my particle traveled. One other thing we should mention is, why in the world did I not have a c in here, right? When we talked about antiderivatives, we always had to put that plus c in there. Why didn't I put the plus c here? Why doesn't it matter which c I choose? Well, now you see, if we look at the capital F of b minus capital F of a, What would happen if my capital F had a plus C in there? Well, I would get a plus C from the first expression, f of b. But then when I do minus f of a, oh look, the c will cancel, right? I'll subtract away whatever c I had. So I don't actually have to worry about doing the plus c because, or even if I did, whatever c I put there, the two things would end up subtracting when I actually did the subtraction to find the value of my integral. Okay, so that's the first half of the fundamental theorem of calculus. The second half is also fascinating, but again, gets used far less often. It says this: suppose you have a nice continuous function, f of t, on some interval ab. Then I could make a function, okay, a function of x, by integrating from a up to x. Okay, now that's weird, right? So I've suddenly got an x as my upper limit of integration, but that's the that's the number I'm plugging into my function. That's just weird, right? But hang with me here. So all in the brackets there, right? That's a function, right? You tell me x, and I can integrate from a to x, and that'll give me a number. So what's in the bracket there really is a function of x. And the question is, if that's a function of x, how do I take its derivative? I mean, again, why would you think you might want to do such a thing? Well, we'll explain that in just a second. But it does look weird, right? And what's even weirder is what's on the right-hand side of that equation. It says it's just f of x. In other words, it's just the thing that I'm integrating with an x plugged in. Okay, that's really weird. Now again, let's think about how Isaac Newton would have thought of this, right? Suppose again that my f were a velocity. Then what's in the brackets? Well, I'm finding the definite integral from a up to x of my velocity. And when you do the definite integral of a velocity, that's telling you how far the particle's moved. So this is how far has the particle moved between a and x, between time a and time x. That's how far the particle has moved. Okay? So that's really how far the particle's moved. That's like telling you where the position of the particle, right? Telling you where the particle is. Now if you take the derivative of that, oh, that's just the velocity again. Right? So this makes perfectly good sense why I should get the velocity. And of course it's the velocity at x, because that's the part that's moving, right? That's where my variable is. Now one thing to notice is this rule works. It's great. It's super simple. If I give you an integral like this, or a function defined using an integral like this, then it's really easy to do the problem, right? I just write down f of x. But notice x has got to be the upper limit of integration. If it's not, we'll have to do some work here. And it's just an x, not like a cosine of 3x plus 7 or something there. If it's something like that, we'll use the chain rule to figure it out. Okay, this definitely needs some examples. So here we go. So here's a function, capital F of x, and it's defined by integrating from 2 up to x, this function, t squared minus 4t dt. Okay? And I want to find the derivative of that function. Again, you can think of that function as sort of like the distance traveled so far, right, from 2 up to x. You can think of it as kind of the area so far from 2 all the way up to x. In either way, the derivative is super easy to find, right? According to the first part of the fundamental theorem of calculus, I just plug x into what I'm integrating. It's just x squared minus 4x. We're done. That's super easy, right? No fuss, no muss, right? So sometimes this freaks people out and they think, my goodness, what have we done here? How hard is this? It's super, super easy. Right? Another way you could, of course, go about this problem without using the second half of the fundamental theorem of calculus and just trying to use the first would be to find an antiderivative for t squared minus 4t, plug in the x, minus, and plug in the 2. Then take the derivative of all that mess. Now, what will happen, of course, is when I plug in the 2 to my antiderivative of t squared minus 4t, that's just a number, so that'll go away. I won't see that in my answer. When I plug x into the antiderivative of t squared minus 4t, then take the derivative, obviously that'll turn me right back into, well, x squared minus 4x. Okay, let's try this again. Let's do a function where now my x is at the lower limit of integration. So I'm integrating from x up to 3 of secant squared of u du. Again, using different variables here just to keep it interesting. I don't want to use secant squared of x dx because I'm already using x for something. So I do want to use a different variable like a t or a u or something. Okay, so how do I make this work? I want to use the fundamental theorem of calculus, but remember that required that my x, the variable here, be the upper limit of integration. So how do I make the x be my upper limit of integration? In other words, how do I switch it? So I put the 3 at the bottom and the x at the top. Well, remember, I can do that. That's perfectly okay. I can always switch those around, but I get a minus sign, right? I get minus what I would have gotten otherwise. So that's great. So I'm going to get minus the derivative now if I switch them. And then what's the derivative if I switch them? Well, I just stick the x into the secant squared, and so I get negative secant squared of x. That's it. Super, super easy. One last one. Let's do this function f of x. Now this is going to be the integral from x squared plus 4x up to 0 of 1 over t dt. Okay, so this one's a little trickier because first of all, my x's are in the lower limit, so I'm going to have to flip it again. But also notice it's not just an x that's my variable. I've got an x squared plus 4x. And so this is like having, one function inside of another. It's like I've done composition here. Instead of just an x, I've composed this with x squared plus 4x. This is a job for the chain rule. So let me write out all the details, but I think you'll see at the end that all I'm really doing is just exactly the chain rule. So the first thing I need to do in order to take the derivative using the second half of the fundamental theorem is to switch my limits of integration around. So I'll put 0 at the bottom and put x squared plus 4x at the top, okay, which of course will generate a minus sign. Right? Now, in order to make this look spiffy here and clear how the chain rule comes into this, let's let u equal the x squared plus 4x, okay, just to replace things. Then when I take the derivative of my function with respect to u, the chain rule says I have to multiply by the derivative of u with respect to x. Okay? So now I just get the minus sign, I get 1 over u, and then the derivative of u with respect to x, which of course is my 2x plus 4, because the derivative of x squared plus 4x is 2x plus 4. Okay, so maybe all the u thing was confusing, right? And if that confused you, instead of making it like, oh yes, I obviously see where the chain rule is happening, then don't write all that out and just use the chain rule directly. So think about this from the very beginning. I've got an integral with the x's in the lower limit and a 0 in the upper limit. That means I'm going to have to flip it, obviously. So that's where the minus sign comes from in the final answer. Now, I need to take my x's, whatever combination of x's all that mess is, and I stick that into the function I'm integrating. So I stick that into the 1 over t. So I'll get 1 over x squared plus 4x. But just like when you take a derivative, if you take the derivative of sine of x, right, you get cosine of x. If you take the derivative of sine of x squared plus 4x, the chain rule enters into the picture. So I would get cosine of x squared plus 4x, but I have to multiply by the derivative of what's inside, right? And the derivative of x squared plus 4x is 2x plus 4. So that gets multiplied right here, just like the chain rule. That's all it is to it.